The phenomenon of the sea that cannot unite has fascinated scientists and observers for centuries. In some places on Earth, two bodies of water meet but do not mix easily. This creates a visible line separating different shades of blue or green. One of the most famous examples occurs where the Atlantic Ocean and the Mediterranean Sea meet at the Strait of Gibraltar. Here, the different salinity and temperature levels prevent the waters from blending quickly. This creates a sharp boundary between the two seas. Another striking example is seen where the Gulf of Alaska meets the Pacific Ocean. Photographs show a distinct line where glacial fresh water meets salty ocean water. The differences in salinity and density keep the waters separate for a time. This phenomenon is called a halocline, where water layers have different salinity levels. Salinity affects water density, which prevents easy mixing. The denser, saltier water sinks below the less salty water, creating separation. Temperature differences also contribute to the separation. Warm water tends to stay above cold water because it is less dense. This creates a thermocline, another type of layering that resists mixing. In many cases, both salinity and temperature differences work together. This forms a pycnocline, a sharp gradient in water density. These natural barriers delay the mixing process, though eventually turbulence and currents can blend the layers. The reason these waters cannot unite easily is rooted in physics. So, water molecules interact differently depending on, things like salinity, temperature, and pressure. These properties actually make the ocean a complex and dynamic system. River mouths are another place where unmixing waters occur. When rivers carrying sediment and fresh water empty into salty oceans, a visible divide often appears. The sediment-laden freshwater takes time to merge with the heavier saltwater. In Indonesia, the meeting point of the Pacific and Indian Oceans around the Banda Sea also showcases these effects. Tidal forces and strong currents create swirling boundaries between water masses. These areas are rich in marine biodiversity due to nutrient mixing. In the Gulf of Oman, similar phenomena occur where the Persian Gulf meets the Arabian Sea. The water layers resist blending due to differences in temperature and salinity. These zones are often visible from space. This separation of waters has cultural and religious significance as well. In the Quran, Surah Ar-Rahman mentions two seas that meet but do not transgress each other. Many interpret this verse as a reference to such natural phenomena. While the boundaries may seem permanent, they are constantly shifting. Wind, waves, and currents eventually promote mixing over time. However, the initial resistance to blending remains fascinating to observe. The unmixing of seas plays a role in ocean ecology. It helps maintain distinct habitats for marine species. Some organisms thrive in brackish waters, while others prefer high salinity. Nutrient exchange at these boundaries supports plankton growth. Plankton forms the base of the marine food chain, supporting fish, whales, and seabirds. Thus, these invisible lines affect entire ecosystems. The study of unmixing seas helps oceanographers understand climate patterns. The ocean's ability to store and distribute heat depends on these mixing processes. Changes in mixing can influence weather systems worldwide. Oceanographers use specialized equipment like CTD sensors to measure conductivity, temperature, and depth. These tools help map the layers where water masses meet. Detailed data allows scientists to model ocean circulation more accurately. Submarine research has revealed even more layers beneath the surface. Deep ocean currents can remain separate for hundreds or thousands of years. These conveyor belts transport heat and nutrients around the globe. Human activity can also affect mixing patterns. Climate change alters temperature gradients, while pollution changes chemical compositions. These shifts can disrupt natural boundaries and impact marine life. Oil spills and plastic waste often concentrate at these boundaries. The different densities trap debris at the surface or below the pycnocline. Cleanup efforts must account for these challenging conditions. Marine transportation often crosses these zones. Large vessels may experience slight differences in buoyancy or drag when crossing distinct water masses. Though subtle, These variations are measurable with sensitive instruments. Fishermen sometimes locate productive fishing grounds near unmixing waters. The nutrient-rich upwelling supports large schools of fish. These areas are economically important for coastal communities. The unmixing of seas also inspires myths and legends. Stories of magical or forbidden waters appear in many cultures. The visible divide fuels imagination and mystery. Despite extensive research, many questions remain. Scientists continue to study how microscopic factors influence large-scale separation. These studies may hold clues to understanding ocean behavior under changing global conditions. Understanding unmixing seas is also crucial for predicting natural disasters. Storm surges, tsunamis, and sea level rise interact with ocean layering. Better models can improve early warning systems and disaster preparedness. In conclusion, the sea that cannot unite symbolizes both nature's beauty and complexity. From physical laws to ecological significance, these phenomena touch many aspects of life on Earth. As science advances, we continue to uncover the secrets hidden within these divided waters.